Hello, and welcome back to my YouTube channel. My name is Professor Kovala, and today I'm going to be talking to you about the difference amplifier. And essentially, in this video, what we want to do is define the difference amplifier, and we want to go ahead and give some basic examples of where we would use a difference amplifier, and then lastly, solve for the V out of the difference amplifier. It says that a difference amplifier is a device that amplifies the difference between two inputs but rejects any signal common to the two inputs. In order to better understand this concept, I'm going to give two examples. And the first example is what's called common mode rejection. And imagine if we have a signal called this V0 and essentially pass it through what's called a single-ended differential amplifier. And then we get what's called differential pairs on the right-hand side. So V1 and V2, where V1 is a sinusoid and V2 is the inverse of that sinusoid. So essentially you can say then that V1, let's say, is sine omega t, and V2 is minus sine omega t. If we consider that there's noise in my signals, so let's say a spike here and a spike here, there's also going to be a spike here and a spike here. And this means that we can say this is plus some type of noise, and also here plus some type of noise. And essentially what we'll prove in this video is that when we pass both our signals through our difference amplifier, so V1 and V2, we're going to get this V out, where if we manipulate our resistors, is basically going to be V1 minus V2. So as you can see, V1 is sine omega t plus noise minus V2, which again, if I distribute this negative sign, I'm going to get plus sine omega t minus noise. So as a result, my noise cancels out, and I'm left with V out equating to this 2 sine omega t. So this is what we mean by when we say that the device amplifies, right? So again, we're amplifying our input signal by 2. All right. The difference between the two inputs, but rejects any signal common to the two inputs. So again, the common signal in this case is this noise. All right. So I hope this first example of where we're trying to go makes sense. So the second application where the difference amplifier can be useful is to measure current. As we know, when we measure current, we need to break the circuit and put a current meter in the circuit to measure that current. In your current meters, there's actually something called a shunt resistor that allows us to measure current. And the idea behind how it works is with the help of the difference amplifier. Essentially, imagine you have a V source connected to an R source, and before it goes to my R load, as an engineer, I'm going to put a very small resistor here called this R shunt. Now, just imagine that after my VS drops across my RS, I'm left with 12 volts here, and here I'm left with 12.1 volts. And in order to have such a negligible voltage drop, this shunt resistor value has to be along the lines of around 100 microohms to around 1 milliohm. So now what we're going to do is put these two signals through my difference amplifier and get a V out, which again, as we will find out, is going to be this 12.1 minus 12, which is essentially 0.1 volt. And so the idea is, since we picked our shunt resistor and we know our V out, we can calculate current. So I is equated to V out over R shunt. And basically, as you can see, as my voltage goes up, so does my current. So then depending on my voltage, we can say that if volts goes above, let's say 0.5 volts, we trigger some type of short that brings it to ground or turns off my power. But essentially, the basic idea in our electronics this is how we can use the difference amplifier to measure current. I hope these two examples make sense and kind of clarify the reasons why we might need the difference amplifier. And if you have any questions or concerns, please leave them down in the comment section below and I'll be sure to get back to you. Okay, so let's go ahead and solve now for this V out. And essentially, we know that for a ideal op amp, IN is going to be equals to IP, which is equated to 0. So the current going in here is 0, and the current going in here is also 0. Where again, this here is IN, and this here is IP. So this here is the first thing we can note. Where the second thing we can note is that for an inverting ideal op amp with a feedback resistor connected to my inverting terminal right here, we can say then that Vn is equated to Vp. So Vn is equated to Vp. Now what we have to do to solve this is write KCL equations at node Vn and Vp, where for my KCL equation at Vn, I can say then that I1 has to equate to I4, where I1 is this V1 minus Vn over R1 has to equate to Vn minus Vout over RF. If we go ahead and multiply both sides by RF, we're going to be left with RF over R1 V1 minus RF over R1 times Vn is equated to Vn minus Vout. If I move the Vout to the right-hand side, I can say then that Vout is equated to RF over R1 plus 1 times Vn minus RF over R1 times V1. So then I'm left with Vout is equated to RF plus R1 over R1 Vn minus RF over R1 times V1. Let me call this equation number 1. And then for the KCL at Vp, I can say that I2 has to equate to I3. I2 is going to be V2 minus Vp over R2, which is equated to Vp minus 0 over R3. This equation here corresponds to I3. So then we can say then that V2 over R2 is equated to Vp 1 over R2 plus 1 over R3 is equated to Vp R3 plus R2 over R2 R3. So then Vp is equated to this R3 over R3 plus R2 V2. And as you can see, this here is basically my voltage divider at node Vp. But I wanted to do this step, the KCL step, so that it's clear and non-ambiguous. Let me call this equation 2. So now we know that from condition number 2, Vn is equals to Vp. So then we could plug Vp into here. And we get that Vout is equated to this RF plus R1 over R1, which comes from here, times R3 over R3 plus R2 times V2, which comes from here, minus RF over R1 V1, which comes from right here. So technically speaking, this here can be your solution. But now let's go ahead and rewrite it in another way that you might see in other textbooks. So what I'm going to do here is I'm going to take my solution and I'm going to distribute my R3 to these two components and my R1 to these two components. So then we could say that Vout is equals to R3 RF plus R3 R1 over R1 R3 plus R1 R2 times V2 minus RF over R1 V1. from our numerator, let's go ahead and pull out an R3 RF. So this first term here, and we're left with 1 plus R1 over RF. Again, keep in mind, if you distribute this here, you're going to get this term. On the numerator, we're going to see that if we pull out an R1, R3, this term becomes 1 plus, again, this is going to be R2 over R3. And just to be clear, this term times this term gives you this term. We go ahead and multiply this by V2, and this is minus RF over R1 V1. And so what we can see is that R3 cancels out here. And essentially the way you might see other textbooks write this equation is V out is equated to RF 1 plus R1 over RF over R1 1 plus R2 over R3 times V2 minus RF over R1 times V1. So now with this, I'm going to write a quick side note here. And I'm going to say that from our two earlier examples, since a difference amplifier must reject a signal common to the two inputs, for example, we had the 12 volts and the 12.1 volt, it rejected my 12 volts and it kept my 0.1 volt. Okay, we say that the amplifier must have a property where V out is equated to 0 when V1 is equated to V2. And this property only exists, if you look at this equation here, it only exists when R1 over RF is equated to R2 over R3. And that makes sense, right? If this here is 5 and this here is 5, 1 plus 5 is 6, 1 plus 5 is 6. So this entire term gets canceled out and this entire term gets canceled out. We are left then with this V out is equated to RF over R1 V2 minus RF over R1 V1. So then we could say then this is RF over R1 times V2 minus V1. So again, when this and this are equal to each other, are common, right? V out is equated to 0. Now, the last thing I want to note is that if all my resistors are the same, so in this situation, RF is equated to R1, and essentially since R1 was equated to R2, so then this is equated to R2, and RF was equated to R3, so this is also equated to R3, we get what is called the subtractor. So V out is essentially just V2 minus V1, and essentially my gain A is simply just 1. So we could just put a 1 here. Just to be clear, we call this a pure subtractor with unity gain. Okay, if you have any questions or concerns, please leave them down in the comment section below and I'll be sure to get back to you. If you liked the video, please give it a thumbs up and please share the video to your colleagues and friends. And if you like the content in which the YouTube channel is providing, please consider subscribing. It really helps the algorithm. Thank you.